So all of the remaining problems, well, almost all of them, are hidden power rule questions, right? They're sort of disguised, right? So if I look at, for example, this question right here, 5 radical x, oops, trying to get comfortable here and I slipped. It's really the same as saying 5x to the 1/2. So if I want to find the derivative there, I would make that move first. And then once I do that, then it's just a matter of taking my power, multiplying it by the coefficient, and reduce my power by 1. So 5 times 1/2 is 5/2 x to the negative 1/2. All right, 1/2 minus 1. All right. Now, I'll show you for this instance, but you probably wouldn't think to use Desmos to check your work for a question like this. It's usually the beefier ones, but I just wanted to show you the skill just so you have it. All right, so to check your work on Desmos, you type in your original function. So in this case, 5 radical x. It'll produce a graph. That's wonderful. You don't actually need to see that graph, so you can turn it off. Okay. Then you type in f prime of x. So right next to the enter key is the comma key, but if you hit the up arrow, you can pull up the apostrophe. And that's assuming you're using a touchscreen, right? If you're using a keyboard, just pull up an apostrophe and you'll have it, right? Type in the x, and what it'll do is produce the derivative graph for you. All right, so this is our derivative graph. All right. Now, what I'll do is type in my derivative equation, but in the form, of y equals. Because I've already used f and f prime, so I don't want to get Desmos's wires crossed. All right, so 5/2 x raised to the negative 1/2. And just make sure that my first derivative, my f prime of x, and my manually determined derivative model map to the same points on the graph. All right, so toggle them on and off and make sure they're going to the same location. If they do, then you did it right. If they don't, then you either typed it in wrong or you did it wrong when you computed it analytically. All right. Now, like I said, you're probably not doing something like this for this question. You'll see some of the questions we do down the line where it's like, okay, that was a lot. Let me see if I did any of that right. You know, that's where the fun comes in. Right? So for the next one, 2 over x could be thought of as 2x to the negative first. So f prime of x would be equal to negative 2x to the negative second. Multiply power by coefficient, reduce the power by 1. All right. Some of them are easier. Let me get rid of these stars. So the next one, power by coefficient, it's already in the right form. So f prime of x, negative 47 x to the 99th. All right. So you don't always have to rewrite before you can get started. This one and this one are already tailor-made for the power rule. All right. Whereas the k of x function, I'd have to rewrite that as 2/3 x to the negative second, because it needs to be in the form of a times b to the, I'm sorry, geez, I almost said an exponential function, a times x to the b power, all right? So the form should be a times x to the b. If it's not in that form, you want to try to get it into that form because that's the easiest shortcut for finding the derivative. All right, so negative 4/3 x to the negative third. Multiply power by coefficient, reduce the power by 1. All right, the last one here, we have to do a little algebra. Very little, nothing too crazy, nothing too fancy. So negative 5 over 9x squared, so I square each part. And then you see it's kind of like a sibling to k of x. It's really the same kind of problem, cut from the same cloth. So negative 5/9 x to the negative second is how I would write it if I wanted it in the form of a times x to the b power. So m prime of x would be 10/9 x to the negative third. And that's really your power rule. I mean, any one of these problems would be sort of a nightmare to do. Nightmare is strong. Very challenging to do if we had to use the limit approach, but using the power rule makes it all better. All right. So I'm going to scroll. This was a cusp example from last class, so we can just kind of gloss over that. We did that off kind of on the side in case you don't remember it a while ago now. So if you want to see this explanation for that, it's in last week's video. So sum and difference rules. The derivative of a sum or difference. So the derivative of the sum or the derivative of a difference, right? That's what that's supposed to mean. Equals the sum or difference of the derivative. Right? What that's telling us is that if I need to take the derivative of the sum or difference of two functions, I can take the derivative separately and then add them together later on. All right. So I'll show you in notation form what I mean by that, just because sometimes the verbalization of it, if that's a word, can sometimes it makes it more confusing, especially when I'm the one in charge of verbalizing. So d dx, again, that means the derivative with respect to x of, let's say, for example, f of x plus g of x, just the plus. That's the same as saying d dx of f of x plus d dx of g of x. Now, sorry, frog in my throat. D dx of f of x, the derivative with respect to x of f of x, that can also be written as f prime of x. D dx of g of x can also be written as g prime of x. So long story short, too late. This monstrous notation here just boils down to taking the derivative of each function separately and then adding them together, right? If the original pair of functions were subtracted, then you would just subtract the derivatives, all right? So that's what it's asking us to do here. F prime of x, 3x squared. And also it's kind of like there's kind of like a subplot here in that this function f of x is also made up of sums and differences. So what this is telling me, and I don't want to go too crazy here, but this is really saying that we could take the derivative of each of these things separately and so on, and then put it all together to make our f prime of x, right? So it's kind of like a double level to this example, where not only am I finding the sum and difference of two separate functions, but since f of x itself is made up as a sum and difference of multiple functions, I got a cubic function, I got a quadratic, I got a linear, and I got a constant function all combined together, I can take the derivative of each piece separately by this same rule. So that's kind of like a cool consequence of what we were working on. All right, so negative 8x, let's see, I want to keep that with the black marker. And then we have that understood power of 1 here. 1 times -9 is 9, or is -9, x to the 0th power. So that's going to just become a -9. Now a constant has a derivative equal to 0. So any constant value is just going to disappear. So that 46, you could use the power rule if you want. There's an assumed x to the 0th attached to it. 0 times 46 is 0. X to the -1st, still 0. I mean, you could do it that way too. But you could also say if something is constant, it's unchanging. If a derivative measures the rate of change of something that is not changing would therefore have to be equal to 0. Right.
Are we gonna put plus C there as well?
Plus C only happens with antiderivatives.
Oh, okay, never mind. Sorry.
No problem. So we'll get there. We're a unit and a half away. But that's an important fact, because really that C that you're talking about, that constant, if you recognize any constant value, you can automatically say that that's going to have a derivative equal to 0. All right. And so when it comes time to find antiderivatives, we'll know intuitively that if you have a 0, the antiderivative working backwards will always give us some constant, any constant. Right. But like I said, a unit and a half away, and we'll get there. All right. So 5x squared. I'm going to rewrite this other piece as -2x to the -5th. So that's my g of x. Now I'm going to take the derivative. Again, we'll do it a piece at a time. We got this one. And then we got this piece. So g prime of x. That's going to be 10x. And plus 10x to the -6. All right, so power multiplied by coefficient, reduce the power by 1. All right, -5 times -2 is +10. -5 minus 1 is -6. All right, so then if I need to figure out d dx of f of x plus or minus g of x, and we're saying that that's the same as saying f prime of x plus or minus g prime of x. I'm going to take my f prime answer, 3x squared minus 8x minus 9, plus or minus my g prime of x, 10x plus 10x to the -6. And depending on what the instructions are, you may have to simplify further, but my general rule of thumb is don't simplify unless you're told to. All right, so in this case, I would just leave it like this because it wouldn't be pretty. All right, you'd have 2 separate answers. I mean, it wouldn't be like anything too crazy. It's just more writing, and if we can avoid it, let's avoid it. All right, so that's the sum and difference rules in a nutshell. There's really not much to it other than to say that we're adding and subtracting derivatives. When we get to product and quotient rule, that's when we're going to get to some more involved processes. All right.
So are we allowed to use this method on the test, or do you have to show the work?
You can do it any which way, as long as you get the right answer. It's fine by me. Yeah, so derivative of sine and cosine functions. So these are some rules. Now, the sine function has a derivative of cosine, and the cosine function has a derivative equal to negative sine. All right, that's where we're going to start our trig journey, but there's more to it than that. But I did want to take some time and show you where these rules come from. Also, I'll take it as a typo. I've been meaning to change this forever. These should be square brackets. I mean, it's fine having parentheses, but the standard notation is square brackets. And actually, it's more appropriately written as d dx square brackets sine of x. Yeah, that's really what it should be. And then cosine x. At a minimum, it's just so I don't have to throw an extra form of notation at you, but also it looks nicer this way. So we have some special trig rules that we need to apply. And here's another typo. I don't know why this happened, but and we've talked about this one before, but this should say equals 1. I don't know why it's not there. So I'm going to just show you really quickly the graphs of each of these. So sine of x over x. So the function y, I'll just say y equals sine of x over x. If we're just looking for the limit, but not derivative, but limit, as x approaches 0, we've talked about the limit coming in from the left and the limit coming in from the right. And we'd be verifying that they're approaching the same value. They do appear to be approaching in both cases a 1. However, once you get there, it says undefined, but we know from our studies of limits that you don't actually have to get there. It's what you're aiming for. We're aiming for the location where the y value is equal to 1. All right. So that's all well and good. Graphically, we have a solution. We know that the limit of this would be equal to 1. Analytically, we don't have an answer yet. Right. I have to show you how to find derivatives entirely in order to show you the rule, the derivative rule that allows you to understand analytically why this is equal to 1. All right. So we wouldn't be able to do this quote unquote by hand until I show you more involving derivatives. And so we'll come back to it. It's a concept called L'Hopital's rule, but when we get there, I'll point it out again. All right. The other rule, 1 minus cosine. One minus cosine x over x also has a limit that exists, but you could see here the point doesn't exist, but the limit exists. So it's not continuous at that location. Right? We know that the limit will exist, but since the point itself doesn't exist, we can't establish continuity at the x value of 0. However, we have enough to say that the limit would be equal to 0. Right? And again, once we talk about this magical concept called L'Hopital's rule down the line, we'll have the answer to that question. Oh, okay. Package coming. All right, so let's differentiate the sine function. Right. So if we have f of x is equal to the sine of x. Okay. My device is going nuts over here. So f of x is equal to sine x, and I want to find the derivative of that. Right. So I would use the limit as h approaches 0 of f of x plus h minus f of x all over h. So my f of x, that's ready to rock and roll. We already have that. I could pop that in for, I could pop in the sine of x for f of x. I need the f of x plus h, which is what you would get if you replace the x in the sine function with an x plus h. All right, so I can make a substitution, limit as h approaches 0 of sine of x plus h minus the sine of x all over h. All right, but it's at this point where we would be in a jam unless we remembered or had access to some trig identities. All right, one of those trig identities is the sum identity for sine. So I'll say rule sine of A plus B is equal to sine A cosine B, oops, plus cosine A sine B. All right, so if you line that up with a sine of X plus H, you'd swap out every A for an X and every B for an H. And it's a sine of X cosine of H plus cosine of X sine of H. And so we get an expansion, but more importantly, we get rid of the sum contained within the argument of the sine function. Right? So bottom line is we now have a way to swap out that sine of X plus H. The limit as H approaches 0 of sine X cosine H plus cosine X sine H minus the sine of X that's already there all over H. All right, all because of that one pre-calc rule that you probably didn't spend a whole heck of a lot of time on. And I gotta say, it doesn't always come up very often. Well, it doesn't come up very often, but when it does, it's pretty important because that's a it's a way of releasing different variables from within a particular trig function. Right. So if you had a multivariable expression like sine of X plus Y, and you wanted to solve that equation or solve that expression, well, it would have to be part of an equation. But if you wanted to solve it for Y, you would need to somehow break it up so that the X and the Y are no longer part of the same trig function. So this would be one way to do that. Right. So anyway, what we can do is regroup because I see that I have a common sine of X. Let me get the blue going on here. So I have a common sine of X here, and part of this expression or this term. So I'm going to rewrite and split the fraction. So limit as H approaches 0 of sine X cosine H minus sine of X all over H. And then separately, I'm going to say cosine X cosine H over H. All right. One of the properties of limits involves a sum rule, which tells us that if you have a sum contained within a limit, you can break the limit up by the sum. Right? So I can write this as two separate limits. Limit as H approaches 0 of, well, all this stuff again, sine X cosine H minus sine X over H. And then as a separate limit, cosine X cosine H. I apologize. Somehow my sine of H along the way became a cosine H. So this, I don't know why. I have no excuse. Shockingly, I caught the mistake, which hardly ever happens. So yeah, this should have been a sine. It's right there in front of me too. Makes it even more egregious. Yeah, so sorry about that. But But yeah, now we're kind of in the home stretch. It just won't always feel that way. You know, because you look at it and say, all right, well, you say we're in the home stretch, but it certainly doesn't look that way. Right? If you look at each expression, both of them contain something that shouldn't be there. Right? Because the limit involves a variable h, the only variable that's relevant to the limit is the h. The other variables don't need to be there. So in this case, the sine function does not need to be there. It can be factored out. All right. So sine of x can be factored out of the whole thing, and it would become sine of x multiplied by the limit as h approaches 0 of cosine h minus 1 over h. Along the same lines, I can pull out a cosine of x over here, and I'd have the limit as h approaches 0 of sine h over h. All right. So this piece, let me get a different color highlighter here. I'm going to go like this light pinkish color. So this piece right here follows this rule. Right? It's the only thing that's different is it's got h's instead of x's, but it's the same rule. So that's going to go to a 1. So this is cosine of x times 1. This other one, this looks close to this one, but it's not quite. So we can actually modify this to go just an extra step to get it to be the exact same formula. So if you take a look at the numerator, I'm going to get another color here. I'm going to go with a light orange-ish color. So if you look at the numerator here and compare it with the numerator there, you see that the signs are the exact opposite. All right, I got a positive cosine. In my expression, they had a negative cosine. I got a -1, they had a +1. So let me factor out a -1. So I'll write negative sine of x here. And when I do that, I'm going to get 1 minus cosine h over h. Now this whole expression goes to 0. What that actually tells us is that we didn't really have to pull out the -1 anyway, because it still would have worked out. Because if I factor out a -1 and then multiply it by 0, it's still going to become a 0 one way or the other. Also, if you're ever unsure if a rule is a rule, pop it into Desmos and have a look. All right, so here we're looking at negative sine of x times 0 plus cosine of x. That's going to result in cosine of x, and that would therefore be our derivative. So that's my f prime of x. So we got there. Took a while, but we got there. All right. At a minimum, this is serious motivation to learn the shortcut rules. And the shortcut rule in this case is just straight up memorization. The derivative of sine is cosine. The derivative of cosine is negative sine. But like I said, if you're ever in a jam and you're like, I don't know, is cosine h minus 1 a rule over h? Pop it into Desmos and see. You know, the picture looks different, but it still has the same limit as you're approaching 0 from the left and as you're approaching 0 from the right. There's a hole at the same location, but that location has a y value of 0. All right, so it checks out. And so you always have that to fall back on. All right. I'll save you from the torture of doing the derivation of the cosine function. Although I can tell you it's very similar. So if you wanted to try that one on your own, you could. It's not, I mean, I can promise you it's not any more challenging than what we just did. That's not really saying much though. All right. So the examples, if you know your rules, we can apply the constant multiple rule. And this is where we really start seeing the benefit of the constant multiple rule. When I look at g of x, I want to think of as pi multiplied by cosine of x. All right. So g of x, not g prime of x. All right. The constant multiple rule tells us that when I take a derivative, I can hang on to any constant multiplier, save it so that I can multiply it in later on. All right. Then take the derivative of whatever the parent function is. All right. In this case, cosine. The derivative of cosine is negative sine. Then multiply them together after the fact. So in this case, we would get negative pi sine of x. Okay. The next one doesn't really have anything too special about it other than to say we have the mixture of a polynomial, well, in this case, a linear function, and a trig function, but that sum, that plus sign tells us that we could take the derivative of them separately. So that x is really the same as saying 1x to the first, multiply power by coefficient, reduce the power by 1, x to the 0th goes to 1, 1 times 1 is 1, and then separately take the derivative of the cosine function, sine function, just gave it away, which is cosine. And then you get right to it in one shot. All right. Then you just kind of put it all together in J, where we would be saying, all right, well, we got a little bit more work to do here. Let's rewrite this. Now, the fourth root of a term is the same as saying to the 1/4 power. You don't have to show the intermediate stuff. I'm just doing it for instructional purposes. But j of x would be 2x to the negative 1/4 plus, and then we'd have 4 multiplied by whatever the derivative of cosine of x is. Okay. Or at least we will do that in a second. So power by coefficient, right? That plus sign gives us license to do this separately. Negative 2/4, so negative 1/2. X to the negative 1/4 minus 1 is negative 5/4. Plus 4 times, and then we take the derivative. We just hang on to that 4. The derivative of cosine is negative sine. And so we don't really have to clean it up, but this is the kind of thing where I just can't resist. Because there isn't really much cleaning to do. Right. So that's really the basic shortcut rules, or those are really the basic shortcut rules. We're going to get into some spicier stuff in a minute, but when you get into calculatory type problems, or when you get into derivatives at particular points, you have full license to use a calculator without restriction. So for these kind of questions, I'm really only looking for a numerical answer. I'm not really looking for the work, although you're welcome to show the work if you're, especially if you're worried about partial credit and things like that. But it's not really necessary. Okay. So I'll leave that part of it up to you, but I did want to show you how to do this using the TI and also Desmos. Right, Desmos is the easier way to do it. All right, so when it says slope of the tangent line, right, it's just saying evaluate the derivative at the given point. All right, so this has points t comma g of t. So this is saying find g prime of whatever the t value is, in this case, pi. All right. So in Desmos, I just need to put my g function in. I'll use x's though. Two plus 3 cosine of x. And then just type in g prime of pi, and it'll just spit out the answer. I don't know why I left so much space. I'll take that as a typo too. All right, so let me show you the TI. If I can get it to open. Come on, get over there. Get over. So you type in your function. In this case, again, 2 plus 3 cosine of x. Now we want the derivative at that point. There's a better way to do it than the directions that I have listed here. So I'm actually going to go through that approach. Right. So I don't, this relies on a graph, and that can be troublesome. So I don't even know what these instructions are supposed to mean. I think I changed something. I don't know. I'm just going crazy. So on the TI, type in the function to the y equals, right? Then quit out of there, the second mode. Then go to math, option 8. Sorry. So math option 8, and it'll bring up this stuff. I don't know how else to describe it, right? So you'll have basically the notation that we've been using, just, slightly different, because that's how TI operates. Right? They got to do everything slightly different. So this is what shows up on your screen. And so what we're going to do is we're going to put in y1 here. Now you could actually just type in the function there, but most of the time we're going to need to do more with the function than just this one computation. So it would be in your best interest to have the function into y equals and then type in y1 here. The way you bring y1 into this computation is by hitting alpha trace. And then, alpha then trace and then select y1. All right, it's a little different on mine, so I just got to kind of do it and just kind of live with it. But you hit alpha followed by trace and then go from there. All right, you're going to type in x here. All right, so in this field here, if I can get it over. Oops, wrong place. I hit the wrong thing. All right, so math, do it again. All right, so alpha y equals, or sorry, alpha trace to bring in the y1. Type in x in the D open field there. Type in an x. It'll automatically change the other open field into an x. So these both will change into x's. All right. If you change one, it changes the other. And then whatever your value you're evaluating in terms of, that goes in the last one. So given in the problem or the question. All right, so here I'll just type in a pi. and it'll evaluate my derivative at that location. Okay, so that's pretty nice. Not as nice as Desmos though, but I mean, if you're given a function that's really difficult to find the derivative of, and we haven't really gotten there yet in terms of like the crazy elaborate ones, you'll find the technology to be pretty useful in those regards, or in that regard. So any question that calls for a numerical answer, you can use technology for, and I leave it up to you which form of technology, because as you know, throughout the whole semester, it's been back and forth between Desmos and TI, mostly Desmos, but TI where applicable, just because I know people are comfortable with different things. So whatever you're comfortable with is fine, as long as you have sufficient work when work is required. All right. So that could be a little trickier on the TI, but you know, honestly, if it means taking a picture of your calculator screen and submitting that, you know, in the end, that's not a terrible idea. You know, like when you're taking a test. So it won't look pretty, but it'll get the job done. And so the next question, it says find the equation of the tangent line, the equation of the tangent line to the graph at the point 5, 0. So we got a point. We just need a slope. Remember the point slope form. Y equals m times x minus x sub 1 plus y sub 1. All right. We have the x sub 1, y sub 1. They already did that for us. All right. The more calculus-y form of this, I'm not going to write calculus-y, but we could write it as f prime of a times x minus a plus f of a. All right, where a represents the x value. The x value of the point of tangency. All right. And this is the moment where I start questioning my own sanity, because part of me remembers making a Desmos for this, but there's another part of me that thinks that might have been in a dream and it never really happened. There's also a third part of me that thinks I might have done it for a different class and never gave you all that information. So I'm just double checking real quickly. In Blackboard, there it is. All right, I did do it. But now I kind of remember doing it as a class. All right, so one of the calculators in Blackboard, if you click on calculators, it says equations of tangent lines and normal lines. All right, it's all set and ready to rock and roll. All right, so let me pull that up real quick. If I can get these. All right. So equations, I just got to go back in my ledger here a little bit. Equations of tangent lines, 6 days ago. Geez, I can't remember anything from 6 days ago. That's a red flag. Well, I can't remember anything from yesterday, so what does it matter? So 3 parentheses, and this is assuming you want to do it strictly on Desmos. 3 parentheses, 5 minus x, close it up and square it. At the point 5, 0, so I'd slide my slider to 5. And then I go down, they gave the coordinate 5, 0, so we're good there. We have the equation of the tangent line, all right, in the appropriate form. That looks an awful lot like the x-axis. All right, we don't need the normal line. The normal line won't plot because it's vertical. So in this case here, we're looking at the line y equals 0 without doing any real work. So that's kind of nice. But I'm sure there's some folks that are wondering how one might go about finding the derivative of something like this. So I'm going to take you very quickly through the by hand approach. So 3 parentheses 5 minus x, close it up, square it. Now, at this point, we have not learned the chain rule. So we wouldn't use the chain rule. Instead, we'll distribute this out. Now, if it's 5 minus x to the 3rd, 4th, 5th, 6th power, I would look for a different technique, but that's not the case here. All right. So distribute it out, or at least this part, 25. The outer is negative 5x, inner is negative 5x, so negative 10x plus x squared multiplied by 3 gives you 75 minus 30x plus 3x squared. Now I need the derivative of that. So I can write, I mean, it's written as y equals. So, I mean, I could change this over to f of x equals, or I could write dy dx as my derivative notation. The constant is going to go to 0. The negative 30x has an assumed power of 1. So that's going to become negative 30x to the 0th, which is really just negative 30. So you could just write the negative 30 if you want. Okay. And then plus 6x to the 1st, or just 6x, either way. This is going to simplify down to negative 30 plus 6x. So that's my derivative. So what I would want to do is compute the slope, right? So the slope here would be the derivative dy dx given that x is equal to 5. All right. Vertical line means either given or such that. So whenever you see that, oh, it also means absolute value. So just to be as confusing as possible. But yeah, in the form of set type notation, it means given or such that. So dy dx such that x is equal to 5 would be negative 30 plus 6 times 5, which is equal to 0. All right, so that's my derivative. But more importantly, that's the slope of the tangent line at the point 5, 0. So if I'm using my point slope form, so if I'm using this one, I'd be saying y equals 0 times x minus 5 plus 0, which would all boil down to just y equals 0. And so that would be the equation of my tangent line. All right. Number 3 shouldn't be here. That's supposed to be in the next unit. I edited, and I guess I missed something. So sorry about that. Another typo. If I wasn't so brutally honest with myself, I would try to make up some line of crap about how I purposely put typos in here so that I can give lots of bonus points. No, I just can't get out of my own way sometimes. It's not a fun way to be, but
I mean, it works out for us.
Exactly. You all get the bonus and I get the corrections, so it's a win-win. All right, so let me stop this video. We'll get into the product and quotient rule now.